Mhm.
Hey, what's up, everybody? As we all know, there was a little bit of a back and forth between myself and Dragnauct on G-Man's channel, which led to another discussion that continued that discussion here on my channel. What I'd like to talk about now is a little bit of a continuation of that on Le Chatelier's principle of how that would affect um, uh, a DNA molecule in an early Earth, and can we lead that to an established system, as in biochemistry? Um, Go ahead and give your thoughts on it, Dragnaught.
Well, it's something that Sam and I and Fiona and MMA artists and Fields were talking about is that Le Chatelier's principle may not be a bit applicable here because what we're essentially talking about here isn't an issue of equilibrium, is whether an acid is going to be combined with something that is supposedly neutral as far as its pH. There wouldn't be any type of reaction there, and that's why I specifically was asking, what type of reaction are you expecting? A specific, reaction, and then we could then decide, okay, well, what type of equilibrium would it, eventually get to? But I think we have to approach it from the aspect of, well, what type of reaction are we looking at here?
Well, you know the type of reaction that would be going down, right? Are you talking about a base reaction or decomposition reaction?
An acid-base reaction?
An acid-base reaction. So you understand how it would play with, for example, DNA in an ocean, right?
Well, yeah, that's why I was asking the salinity. Now, if we're just talking about H2O by itself, H2O is neutral, so it wouldn't be an acid-base reaction.
Well, H2O actually acts as both a base and an acid for an acid-base reaction.
It acts as both. Maybe you can elaborate a bit. Maybe
Because
I'm
of the
not.
hydrogen. Well, a base is anything that accepts basically a proton, and a an acid is anything that would donate a proton. So, because of the hydrogen inside of H2O, that is a very good promoter for both aspects.
Well, it just doesn't.
For example,
Go ahead.
if you had hydrochloric acid and you added a base of H2O, it wouldn't really change. It wouldn't really change too much. You would call it H2O or H3O plus because of the change of the electron.
Yeah, the hydronium content hydronium or the there's another isotope I'm thinking of. The pH would change depending on whether the proton is taken away or added, but that also depends on the oxidation state of whatever else is in there. So just because there is a molecule in there that has hydrogen attached to it doesn't always guarantee that it's going to go one way or the other. That's dependent upon the molecule itself, and that's basically what I'm trying to get at, is that if we're just talking about water and we're putting something that's acidic into something that's just H2O by itself, that's not really going to degrade the quality of the acid. If anything, it'll move it more toward neutrality than anything else.
No, and then there's a lot of things that we have to cover here. To begin with, when you're talking about an abiogenesis type of environment, there's a lot of volcanic gas, different types of chemicals that are in there. But if we're going to be talking about an acidic base, like H2O is, the only way that you're going to have a change in, or I wouldn't say a change, but a protection of that molecule, keeping it from breaking down to its more constituent parts, is in an aqueous solution. But you know the problem with an aqueous solution, right?
It depends on what the aqueous solution is.
Well, do you know what they use to try to protect an aqueous solution, to protect the DNA and keep it from breaking down?
Sure, they have certain preservers, just like you have what they call vaccines. They'll have thimerosal as a preserver.
Okay, well, typically, what do they use? They use salt, right? Salt is supposed to help keep it from breaking down, but it doesn't stop it from breaking down. It just slows down the process. And what else would they use in an aqueous solution?
They use what type of molecule are you referring to when you say salt?
Well, I'm talking about in DNA. DNA is a sugar phosphate molecule. So the way that they protect DNA in an aqueous solution is by what? What do they put inside of that solution to protect DNA?
It could be any number of things, but when you say salt is just not the sodium chloride we have on the counter here. There are different types of salts out there. So that's why I'm asking you specifically,
no.
what salt are you
There's
referring
different
to?
types of salt. There's bromine that comes down from the bottom of the ocean floor when during the summer, or during the winter, when in Antarctica, the brine, thousands and thousands of pounds of brine goes into the ocean floor. So salt in general, but salt is basically what they use to try to keep the DNA molecule from breaking down to its more constituent forms, but it doesn't stop it from breaking down.
Hold on just a second, let me look this up, because there is a certain solution you use for DNA preservation, and I'm not sure if it's necessarily the same type of salt that you're referring to, because we can have salt that precipitates out of, you know, any number of chemical reactions, but that doesn't mean that that salt is going to react the same way as any other salt. You see what I'm saying?
Well, it is going to act the same as other salts, of course, but you understand that, right? That it's salts that they're using. It doesn't stop it from breaking down. It just slows down the process.
Well, no, you're not going to have something unless you like cryogenically freeze it.
Okay, so let's move forward into this a little bit. How is it that you're going to be able to get an established system of DNA? Let's just say that, for the sake of argument, that DNA was going to be able to be protected. How are you going to get DNA, thymine and cytosine? You know what that is, right? It's a ring-based chemical.
When you're talking about denning, you mean C5H5N5?
Yeah, I'm talking about DNA. How, you know, the chemical structure, but you know, it's
different constituents to make up DNA: the guanine, cytosine, thymine, so on and so forth. Yeah, the pyrimidine
bases and the purine bases, the heterocyclic bases. You understand the chemical operation behind that, right?
Sure, I understand that. When we're talking about the interaction between the molecule itself and its environment, we have to understand that the fact that you can dissolve one into the other does not mean that it's going to compromise its structure.
What do you mean dissolve? What do you mean dissolve one into the other?
So if you have, when you dissolve something, doesn't mean that it actually it loses its how can I say this? Its integrity. So if I have cooking oil and I pour cooking oil into water, I can actually strain out that cooking oil and reuse it. It doesn't just, you know, become unusable. Does that make sense?
Well, actually, I would disagree with that wholeheartedly. If you're having DNA,
they're admissible.
If you're having DNA breaking down to its more constituent parts, and you're going to say that you can reuse that, I don't know a system that at all is totally run on only you know, the chemicals and the broken down parts of DNA. Okay, it usually takes sequences of a DNA strand to work and function of any established system.
Okay, so when you're saying they break down, that means that there's a reaction happening, yes?
Yes, well, there's a reaction happening which is causing it to break down. The reaction would be the additional electron, or the hydrogen atom without the electron in the water.
So are you talking about reduction or oxidation?
I'm talking about the breaking down of the DNA molecule. Okay,
so then that's a different type of, that's an actual named reaction. So if we have, like, maybe I can just show you. Boom, here we go.
Well, again, I mean, can you give me an example of a DNA of any type of established system that's operating, any type of established system at all that's operating, that on just basically the broken down constituent parts of DNA?
Well, that's what I'm asking. I'm having a hard time with you asserting that something's breaking down, but we're not being specific as to what type of reaction is happening. Things don't just break down and we don't have an account for it, or we don't have a name for it.
The problem is that we just broke it down pretty much in detail just now about an acid base and a base reaction with the changing of a proton.
Okay, and, well, that's
hydronium ion. So I mean, this is we just went through this. So I'm trying to move forward into this, and I'm trying to ask, okay, so since we're dealing with a broken down system, all right, what system do we know of that runs on broken down parts of DNA and not
Okay.
not a strand that has sequences of DNA in it?
Okay. And when you're saying broken down, does that mean that there is a chemical reaction? Yes or no?
Didn't I just answer you that on that a few minutes ago?
I'm trying to go through it because every time I continue with my line of thought, you interject, and I'm trying to pin down what this reaction is. I mean, it's either a gas forming reaction, a combustion reaction, an exchange reaction, an
It
acid
would
base
be a base
reaction,
reaction. You can look at it would be a base reaction, I
a
believe, and you
base
can probably
reaction.
call it. You could probably look at it as I forget the word for it. Um, decomposition reaction.
A decomposition reaction. Okay, that's something I can actually sink my teeth into. Decomposition. So, what type of environment are you're saying that the environment is too basic and that it would just decompose into its constituent parts?
Now, again, the question is if you can just reuse that material after it's broken down, what life would be able to use a broken down molecule like that?
Oh, well, we do have these things called viruses that use parts of our DNA in order to propagate
But the
itself.
problem is with viruses, they're not living organisms. On top of that, they are dependent on host cells to be able to reproduce and survive.
Well, they're pseudo-living technically. They've actually been upgraded. They have the ability to alter our DNA through, horizontal gene transfer. So they're much more hardy than people believe. But the ones that we see now were probably not the ones that of ages and ages ago, with just an assumption that they've just remained the same.
But you understand that it's a virus needs a host cell to be able to reproduce. On top of that, a virus has a protein coat, and usually whenever proteins are developed inside of a cell, that's because of the process of DNA to RNA to protein.
Yeah, we actually have some that don't have that coat. That coat's just something that more than likely developed over time, but that's kind of
okay. Well, can you give me an example of that?
An example of a virus type entity that doesn't have a protein coat?
Yes.
Just a second. Virons.
Virons. Can you send a link on the side and can you read it for us, please?
Let's see. These viral particles, also known as, I'm probably mispronouncing it, virions or virons, consisting of 2 or 3 parts, the genetic materials either made up of DNA or RNA, long molecules that carry genetic information. Nope, I'm reading the wrong one. Hold on. I think I'm reading. Yeah, I was reading the wrong one. Where's the Mimi virus? I might have been thinking of something else. Oh well. Anyway.
Yeah, because they do have protein coats. Most viruses do. So, I mean, how can you move on to chemistry then? How can you say that? How can you say that? Well, we can use broken down DNA as a material for life. There's no example of that anywhere.
Well, here's the thing. When have you heard me saying that I know for certain that abiogenesis in the way that we see it nowadays is the exact way that it happened and ages past?
Okay, well, let's go back then. How do you think that abiogenesis happened, and what evidence do you have that it happened that way?
Have you ever heard me stick by abiogenesis?
Well, the other day you mentioned something about, for example,
DNA isn't broken down,
silicon.
by the way. I keep forgetting it. I keep forgetting to mention that.
I'm sorry?
The DNA isn't broken down, by the way. I keep forgetting to mention that.
DNA isn't broken down. What do you mean?
Not in the way that you're describing. DNA doesn't break down like that.
And in what way am I describing it? Are you talking about in an ocean? Or are you talking about in life or needing for life? You got to be a little bit more specific.
In the scenario that you're presenting, that you place it in some type of salt, I think you said, and it just breaks down. It loses a proton, but it doesn't just break apart into it's
No, yes,
pure
it does.
elements and then just
DNA, and for people that are watching this, I hope that you go and check this out. DNA is water soluble, and especially RNA is. Check out the reasons why. It would break down in any environment unless there are some elements inside of those environments that can keep it from breaking down. And usually, those things that are used, like ethanol, are harmful for life. It's a type of alcohol that people don't know about it. And for example, salt. Salt doesn't uh, stop it from breaking down either. It just slows down the process.
okay. So we do know that it does not break down when it's in a solution. Or is that something that's controversial?
Solution is a solution also has chemicals in it that would be harmful for life. So it's unrealistic.
Oh, so a solution. So we're not able to perform gel electrophoresis on it.
Well, we are able to do that in a solution.
You just said we can't do it in a solution.
No. I told you that we can do it in a solution. The
Oh,
point
okay.
is that inside of a realistic scenario, and the realistic scenario with all these gases in play, it wouldn't work. Most of the chemicals that are being used are harmful for life. And salt, as you mentioned before, salt doesn't stop the process from happening. It slows it down.
Okay, when you say salt, you're not being very specific as to what salt you're referring to. And I mentioned that earlier. Sodium
Okay.
chloride is a salt, but that's just one of many salts that is out there.
Okay, so you're saying that there's a salt out there that can stop this from happening? Because as
No,
far
I'm
as
saying
my
that
reading
you're
goes, there is
throwing the
absolutely
word
no
salt in there as if all salts behave the same. Half of them don't even have the same electronegativity. I keep
Okay,
saying
here's the
electronegativity, but
point.
they don't have the same ability to combine with other elements because they have a different valence.
Okay, well, here's the problem here. Every single salt in every single place that I've read from, every type of aqueous solution that is used, salt has never been demonstrated to stop the process. They have to introduce another element like alcohol into it to stop it from breaking down. It can only slow down the process. So if there's something specifically that you're thinking of in an aqueous solution, which you brought up, then I would like for you to bring it up here so that we can investigate it.
Okay, so would you like me to look up what people use in DNA tests as far as their solution in order to preserve it?
Yes, absolutely. But you know what? We just got off topic again because we were going to go into the silicone because you said that you don't hold to, for example, abiogenesis. You don't defend it. Can you reword how you just said that earlier?
Wait, say it again.
How did you say your approach would be with abiogenesis? We were about to go into there, but then it changed into different topics because you said something about salt.
Okay, as far as abiogenesis, the way that we look at abiogenesis, it's for me problematic because we're in an environment where everything has had to have hundreds of millions of years of trying to evolve and trying to become stable. For me, when I look at abiogenesis, I tend to look more towards panspermia and astrobiology because there you have environments that are more conducive towards this line of thinking and this type of research.
Well, I'm sorry.
So,
Repeat what you just said at the end there.
so for me, I think we need to look towards astrobiology and also panspermia as far as how we do this research. I think currently us trying to do research in this arena, in this world where it's had hundreds of millions of years to evolve, I think that's a bit misguided. And I think we should actually put research into studying the environments on planets that are near inhospitable for life in order for us to study what life was back before this planet was hospitable.
So you think that life started on some other planets and came to Earth?
Well, the constituent parts of life, the key elements, because, we have all kinds of asteroids and comets sprinkling us with all types of cool stuff as they pass by. And some of them end up landing here and enriching the soil around it. So, of course, the universe provides.
Okay, so all right. So what you're basically doing there is you're moving the problem to a different location. And I don't think that really even deals with the problem.
That doesn't deal with the problem if a problem is how does life begin in a near inhospitable arena, and then I say we're actually in the wrong arena and that we should look into an arena that suits what the scenario is, how is that moving it?
It's moving it because it's not answering the question. It's saying that, well, life came here from some other place. I mean, or the ingredients at least came here from some other place. Well, how are you going to get the ingredients to start? I mean, even if you're going to say that the ingredients came, and if it's moving into a hostile environment, you don't get rid of the problem even still.
Actually, you do have if you have a planet and this planet is rich in only certain elements, like we have what is that planet Titan, which is mostly liquid but methane. That's not really conducive for life. So you need life to kind of have let's say, a jump start. So you have bits and pieces of sprinkled elements here and there that would actually provide what's necessary for life to begin, just as birds carry pieces of seeds in their dung, and then they go and they defecate over certain islands in Hawaii, and that's how we get the fauna over there. I mean, it's not something that's really controversial.
Well, I think this is kind of controversial because we don't know of any other place in the world or in the universe where life can exist except for this one. We know that some chemicals that are necessary for life can come in through some meteors, for example, but coming into this planet and entering into the environment that is as hostile as it would be in an abiogenesis environment, it doesn't change the problem. I mean, it's still there. So I don't really think that you're making any point right now.
Well, I mean, it's still like it's an ongoing search for the answer. It's nothing that we have down pat, because this is technically astrobiology is a new field. And so we know that we have organic compounds on commoners, on meteors, and on other planets, just not in a great abundance like we do here.
Well, see, here's the problem with that. Here's the problem with that. It doesn't matter if you have the chemicals that are in some sort of other planets. I mean, we know that we can produce chemicals in certain environments here, and even in volcanoes, certain organic compounds can be produced inside of some volcanoes. But there are also other hazardous materials as well that hinder any production of life that could happen, as far as we know it. So, I mean, even if you are able to produce, let's just say that you're able to produce proteins, which I think I'm giving too much credence in that direction, but let's just say you were able to produce proteins. Okay, well, then how do you produce an established system of life?
Well, for one thing, we need to look at what we have already. Do we have examples of things living in or near volcanoes or the hydrothermic vents or anything like that?
Well, they are some that live close to there, but the problem is that they are established systems already. And what we're talking about is something as fragile as DNA and RNA.
So have we found anything living like on a comet or anything that's, in a near inhospitable environment, such as the reaches of space?
We found certain chemicals inside of some comets that have come here to this planet, but that's not life.
What about tardigrades?
No, well, we have not found any type of life in any other planet coming over here to Earth.
Really?
Yes, we've sent some bugs and certain things into space, and they can survive the vacuum of space. For example, I forget what the name of them are. They're like these little bugs, water bears or something like that. They can survive the vacuum of space. But we have never sent anything, or we have not had any life come here from any other planet on Earth.
So if we know that we have the capability of these things to be able to survive the reaches, and even something as multicellular as a tardigrade, and we have the really small extremophiles that can survive, wouldn't it? Well, I mean, you kind of see where I'm going here. We have both multicellular and single-cellular organisms that can survive these extreme conditions. Again,
I think I just answered that question, and the point would be is that those are established systems. That organism is already established. It's a living organism. It has the capabilities to already survive. With DNA, for example, it doesn't have that. For example, with DNA. DNA is inside of our bodies. DNA in our bodies tend to be 70% water, 70 to 80% water. I don't remember exactly, about 70 or 80% water. We're mostly water, but our DNA doesn't break down the same way that it would in a natural state or in an ocean or something like that, because it's in an established system. It's being utilized. It's protected. Without being inside of our body, what do we need? Like we've been bringing up, the aqueous solution. So it's going to have to be protected. So again, it doesn't really matter if there are organisms that can't survive. They are built to survive there. They are built to live.
Oh, I like the language used. They're built to survive there. It's not that they themselves have overcome extreme conditions and adapted. They've been built. It's very convenient.
Well, well, let's get back down to the biochemistry of it all. Then you've heard me bring up things like motors and turbines. The reality is that we don't have any demonstration that's total chemistry by itself can lead up to that complexity outside of an already established system, other than intelligence doing that. So
is there an intelligence that causes
if you're going to say that I like the way that you use that language, well, I think the language is connected with our cause and effect of what we actually see in reality.
I think our language is connected to the fact that us humans are subject to apophenia.
No, I think it's a bit of common sense and rational thinking and connecting things, like I said, with cause and effect.
You do know that the universe doesn't comport to our intuition. It's the very opposite, in fact.
That is totally irrelevant to the point.
That's actually what you're saying. If you're saying that you're just using
the fact of the
logic
matter no, you're not even really touching on anything right now. You know what a scientific theory is, right?
No, please tell me what a scientific theory is. True.
A scientific theory is an observation based on the natural world on repeated testing.
Okay.
A repeated observation. Do you disagree with that?
No, sure. Let's go with that.
So what's important in some tests?
Oh, the ability to take statistical analysis and determine the probability of an event and its margin of error and its reproducibility.
So the more complex a system is, would you say that it is more and more improbable?
Not necessarily.
Okay, can you give me an example of a system that is not probable, that is not complex?
It's not complex. Like, how are we defining complexity? That is such a vague term.
Well, you know how I define complexity all the time. I wouldn't say that complexity would be that equated to a snowflake being formed, because that can be formed under a fairly simple process. I'd say that complexity as in multiple components working together in a coordinated fashion, like cars or like the cell, that would be
ants.
Something that I would say is complex. Or ants.
I mean, digging holes in the ground isn't really that complicated, but they work together to do it. I wouldn't consider that complex.
Yeah, the thing that they're doing isn't complicated, but the thing itself that is doing it is what is complicated.
I think that's in the eye of the beholder, honestly.
Well, with all due respect, you keep on saying statements like, well, how do you know that it didn't just evolve this way? Why do you got to use the language that it builds? Well, because realistically, like I said before, these systems that are used to be in this established system, like motors and turbines, they come from creative intelligence. And our repeated observation is that they come from creative intelligence, which is important, and a scientific theory. So this is the reason why I say it was built. And I am more justified in saying that it is built than you saying that it evolved this way, because thus far we don't have an alternative place to where this actually comes from. With abiogenesis, the results are trying to be produced. They're trying to be manufactured. Okay,
so your assertion is that you've observed things, and for you, minus the apophenia that we're all subject to, it is the result of something, an intelligence that somehow
do you know what apophenia is? I don't know if you're using that correctly here. Do you know what apophenia is?
Please tell me what apophenia is.
It's basically supposed to be pattern seeking.
So if I'm saying that you're seeking patterns and then you're drawing conclusions, how does that detract from what you've already said?
Because that wouldn't be the same thing with what we're saying here. I can say that I'm looking at clouds in the sky and they look a certain way. They have a certain shape of a car, for example, but that's obviously not a car. And the reverse, with ATP synthase or with a motor, the bacterium flagellum, it has bushings, bearings, and so forth. It is built and it functions and it operates the same way as our motors that are built. The only difference would be proton motive force. It is the exact same way in pretty much all dimensions. So that wouldn't be pattern seeking, but I would say that in the reverse, that it is pattern seeking when you're looking at evolution, because you don't have any demonstrated cause and effect to produce any of these mechanisms. You're only seeing patterns through the fossil record.
If I don't have anything to reference, and I do have that, that statement contradicts itself, right?
Please show me how it contradicts itself.
You literally just said, I don't have anything to use to seek that type of pattern, but then you say I referenced the fossil record.
No. I'm saying that you don't have any way to prove a cause and effect where I have to show that, okay, these things weren't built this way. It took time, millions of years for this function to become developed. So the only thing that you have is pattern seeking, looking at already established systems in the fossil record and saying, look, this one came from this one, but there's no cause and effect to produce or to prove that this one came from the other.
I would disagree with that. I actually say that the fossil record would provide us with a good template to make predictions, and that if the predictions are false, then we can discard it. If the predictions are true, then we can accept it.
Okay, irrelevant. You can make predictions.
It's very relevant.
You can predict all sorts of things, but it doesn't mean that you can predict a cause or effect. For example, proving and demonstrating that new anatomical features across these different species across the board can be developed is different than saying, well, I predict, like for example, look at this, retroviruses. Viruses, we see a lot of changes happening within retroviruses, but so we can make predictions there, changes happening to an extent. But obviously those changes that we're seeing, we never get to see if any of that could lead to some sort of new anatomical feature and function, like we would see when the differences between birds and reptiles, or reptiles and mammals, or fishes, or whatever.
Okay.
All right, so
I'm really trying to see what you're getting at here.
The last discussion that we had, you brought up what was it? Silicon dioxide, I believe it was, right?
And you told me that I was wrong when I said the silicon dioxide is the 90% of the Earth's surface.
No, I didn't say that you were wrong about it being 90% of the Earth's surface. I think that what happened was that you brought that up as a sort of disagreement as that being used by God or a creator, and that relating with the oceans as well. Can you expound on that?
Sure. When you have this claim that the creator of the known universe somehow used an element that's less than 10% of the Earth's surface to create all of human beings, well, the progenitor for all human beings, I find it a bit odd. Since,
why?
Well, if you have the dust of the earth, which translates to afar, and that literally means the dust from the earth, the ground, the dirt, the surface, you don't have carbon just sticking up out of anywhere. If you were actually to take pounds per million and dig up some dirt, see how little carbon is in there compared to all these other elements, it seems a bit improbable, just according to what we know about soil composition.
Well, there's a couple of things wrong with that. Obviously, silicone isn't necessary for life. The tool that's needed is carbon, and carbon is found inside of the earth. It's not as wide in variety as silicone is, obviously, but silicon dioxide, silicone obviously isn't by itself, but carbon is found inside of the soil as well. I believe humic acid is an important part of plant production. You need to have that very complex hydrocarbon inside of the soil. So, I mean, this is the type of thing that I'm saying. I mean, you tend to go certain places with the things that you're saying, but they never finish or lead to a specific point.
Well, it helps when I'm not cut off every 2 seconds.
Well, have you been cut off here? I mean,
well, you're saying
the last discussion, I understand. Well, see, you just cut me off there. The last discussion that we were on G-Man's channel, you seem to, I don't want to be rude, but you seem to like not go anywhere. And I can understand that there was a lot of people interrupting because, you know, it was chaotic. There was a lot of different people, but there seems to be no points to saying that. I mean, why would you say that about silicone? Why
would I make a point that someone's saying that you have a particular element that's used to create a particular thing and it not being readily available? You think that doesn't have a point?
Well, again, it's like I explained before in the other hangout. That's like saying that we have a toolbox full of flat-headed screwdrivers. Why isn't the person that's going to be using those tools not not using the flathead screwdrivers and instead chooses to use a wrench because that's the tool needed for the job. So it's really silly to say, well, why do we have silicone here available, and why would God make life here on this earth, and why, most of it's silicone? Well, it doesn't matter. He didn't need the silicone. He needed the carbon because carbon is tetravalent and has the ability to make more of these complex molecules that silicone can't. So it's just, I don't think that there was really any point to that. And it was also a mistake because it's true that there is 90% of the Earth's crust is silicon dioxide, but there's also an additional 90 elements. And even though they are few, many of them are needed for life, and they are cyclic hydrocarbons.
Okay, so what your analogy fails to acknowledge is that we measure stuff in the soil by parts per million. So it's not a toolbox. It would be you throwing one tool that you need into an entire garbage dumpster full of tools, trying to find that one. That would be a more accurate description of what's happening here.
No, that actually wouldn't. What I said was exactly what the point was. I mean,
that's a false
analogy. You have carbon. I mean, it's really silly. I mean, why are you going to say that silicone is? Why would you even bring that up about silicone? If you understood the composition of the Earth, you would know that there was an additional 90 elements, and obviously, silicone isn't used in any life because carbon is the basis of all life and existence as far as our knowledge goes. There was no silicone-based life. But I'll let you have the last word. I don't really think we're going to go anywhere with any of this.
Probably not, but I thought it was an interesting discussion. People watching thought it was very interesting. They sent me some messages. So you see what I have here, right? The water and the adenine.
No, I do not. I have my. I don't have.
Are you on your phone?
No, I don't have my camera on. My.
Oh, you don't have it turned up?
I don't have.
You muted yourself. There you go.
Well, I got to actually end like right now anyway. So, because I got to be at work early today. So, I mean, I wish I could talk longer. That's why I said that we can only talk for about an hour and a half or so. But thank you for talking with me. See you guys later.
See ya.